Okay, so this idea is really just working with a constant force. So I was talking about constant force here. What we want to do next is we want to think about working with a variable force. But before I talk about that, I want to take a slight detour. I want to think about work in terms of the area of a rectangle. So let me draw a quick picture here to help you understand what I'm trying to get at. Because so far we haven't really done any calculus stuff, but you're going to see how calculus ties in. So we're going to have the x-axis be distance. We're going to have the y-axis be force. Okay. So we had said that we were looking at a constant force F over some distance d. And what I want to do is I want you to imagine, okay, here's 0, here's whatever d my distance is. Because my force is constant, you guys know that constant functions are just horizontal lines, right? So if you think about what does F times D mean, you could think, oh, that's really the area underneath this curve that's just a horizontal line. So what I'm trying to say is that this area is the amount of work done by a constant force. Does that make sense? So so when we look at the idea of investigating the work done by a variable force, a variable force means that the force changes. The force changes depending on what your x value is. So in this particular situation, maybe I could draw a different picture. I can draw a picture that looks like this. This is still our force axis. This is still our distance axis. But this time, when I draw my force, perhaps the force increases the further I go. And then let's say we're going to D over here. So you can see we don't have a constant force anymore. It's changing. It's smaller for small values of D, but then as D increases, it gets bigger. I'm not sure if you can predict where this is going, but what we're going to do is we are going to approximate the area under this curve using area of rectangles. So what we're going to do is we're going to chop this interval from 0 to D up into n pieces. Okay, so you have we're going to approximate work done with n pieces of constant work. So what you could do is you could calculate work with this, approximate it with the right endpoint. Something like this. Okay. And when we approximate the amount of work done by imagining we have n separate pieces of constant work. I don't know why I have that word force there. Ignore that. Well, what's that going to look like? What's going to look like is we're going to have the sum of n rectangles. We're going to take our force and we're going to evaluate our force at some unspecified point inside each of these subintervals. We're going to call that point xi star. And then we're going to multiply by a little bit of distance. So that little bit of distance is what we call delta x. I'm sorry, delta d. Well, we're on the x-axis, so we'll call it delta x. Okay. Delta x like this. And delta x is just the difference of the two endpoints divided by n. I'm hoping this looks a little bit familiar to you. Then we can find the actual amount of work done by letting n go to infinity. And when we do that, the work is going to be equal to the limit as n goes to infinity, the summation as I goes from 1 to n, f of xi star times delta x. So this is the limit of these guys. And these guys, you can think of those as Riemann sums, which is what we studied in 4.2, I think. Okay. Now, what we're going to do is we're going to think of this limit as an integral. Sigma is the Greek letter for s, so we put the s here. We could take f of x. Delta is the Greek letter for d, so we'll put a dx over here. And then we can go from whatever point to whatever point. And this is our work formula for a variable force. Does that make sense? So now you can see why this is in the calculus section. The constant force situation is what we do in sort of high school physics, and the variable force situation is more of a calculus idea. So let's take a look at example 3. Example 3 says, when a particle is located x feet from the origin, a force of x squared plus 2x. So right away I can identify this right here. This is my my force function. And that force is changing depending on what x is. I also look at this, I can see we're working with pounds. That's the US customary system. Okay. The question is, how much work is done in moving it from 1 foot to 3 feet? So I'm pretty sure I wanted to mention that these were feet. Okay. So we just set it up, right? Work is equal to an integral of your force function. And you're going to do that with respect to x from A to B. In this particular case, you know what? I wanted to make sure I showed this dependent on x. So let me put a f of x like this. So in this case, we have the integral from 1 to 3, x squared plus 2x dx. And when I integrate, I have to find the antiderivative. So this will be x cubed over 3 plus x squared. We evaluate that from 1 to 3. When I plug that in, what do I get? I get 27 over 3, which is 9, plus 9, which is 18, minus 1/3 plus 1. 1/3 plus 1 is 4/3. Okay. So I want to put it under a common denominator. So I can multiply top and bottom by 18. I'm sorry, multiply top and bottom by 3. So 18 times 3 is, 54 minus 4 over the common denominator of 3. I get 50 over 3. And my units are foot-pounds. This is the amount of work done by this variable force. Does that make sense, everybody? All right.